Welcome to the section 2.9 pre-class video assignment. So section 2.9, we are looking at solving systems of equations. Now, that's what it says in our book's title here, but of course we mean DEs, not algebra equations. How do you solve systems of differential equations? And our ultimate goal here is to set up an elimination method to do this. Systems, some preliminaries here. Systems of differential equations do arise naturally in a few application situations. The classic example is mixing tanks that are connected to each other, interconnected mixing tanks. There are other examples. So you can have spring mass systems where you have one mass hanging from a spring and then a second mass hanging from a spring hanging from the first mass. So this is would also be leading to systems of differential equations. And so there are some, again, natural situations where these arise. So we're going to talk through, this is probably the, I don't know, conceptually the most straightforward example of a system. So let's talk through setting up a system of equations for interconnected mixing tanks. So we did look at a single mixing tank previously. The key idea, which is still very important here, is this is our modeling idea for mixing tanks. Yes, the rate of change of the amount of whatever it is in the tank, usually salt or something, the rate of change of the amount of salt in the tank is equal to the rate of salt in minus the rate of salt out, if it is indeed salt or whatever it is. So this applies now. This still applies, but this would apply to each tank. This concept applies to each tank, but otherwise this is, again, with a bit of critical thinking, this is not too difficult. So we're going to consider the following interconnected tanks. Both are 24-liter tanks. They both contain brine solution, which is being circulated and mixed thoroughly. And again, mixed thoroughly, we are to interpret as meaning mixed perfectly at all times. And basically we have this, yes, we have a 24-liter tank. We have a 6 liter per minute inflow. We then have 8 minutes per liter flowing out of tank X and into tank Y. We have 2 liters per minute flowing back again. So notice, if you're looking at just tank X, you've got 6 liters per minute in and 6 liters per minute net out. So we maintain 24 liters in tank X. Similarly, we have 8 into tank Y, 2 out of tank Y, and 6 out of tank Y. So the net effect is that tank Y has a constant 24 liters in it. So this is certainly the easier setup situation where the flow rates at least balance out. So the idea then is to say the following. Let's say X of T is the amount of salt in dissolved in tank X. So this is not brine solution, it is actual salt in kilograms dissolved in the tank. So let X of T be the amount of salt in tank X, let Y of T be the amount of salt in tank Y, and our goal is to figure out functions for X and Y that model the amount of salt in this situation. So let's see, we are told, again, we have these brine solutions, and we are told that the 6 liter per minute inlet to tank X, so the in for tank X, is actually fresh water. Yes, fresh water is being pumped into tank X. Everything is being mixed thoroughly, going this way, and then being pumped out again. And again, we are to solve for X and Y. So to set this up, we need to look at both what is the rate of change of salt in tank X. The overall rate of change of salt in tank X is rate of salt into tank X minus rate of salt out of tank X. Again, as you remember from our single tank case from previously, section 1.11, rate of salt in is the flow rate of the fluid times the concentration. So flow rate times concentration gives us rate of salt in, and similarly, flow rate times concentration gives us rate of salt out. So we have to consider our inputs. So for tank X, what are our inputs? We have a 6-liter freshwater input. So that is flow rate is 6, concentration of salt is 0. We also have this input to tank X. This is a 2-liter per minute input. So that is a flow rate of 2. And then we have to multiply it by the concentration of the salt heading in this direction. So the logic here is the concentration is always changing. It depends on how much salt is in the tank at any moment. But we have a designation for what that is. We're calling that Y. So at any moment, the concentration in tank Y is the amount of salt in tank Y divided by the volume of tank Y. So this is your concentration. Amount of salt divided by volume is your concentration. So flow rate times concentration, that is still an in, so it is a plus. And then we have a flow rate out. This is our only out of tank X. Our only out of tank X is a minus. Flow rate out is 8. Concentration going this way is the concentration in tank X at any moment, which is, again, amount of salt in tank X divided by volume of tank X. So this is the formula for tank X. This is the model for tank X, I should probably say. Now you can think through tank Y in a very similar fashion. Tank Y has 2 outputs and 1 input. The only input to tank Y is flowing at 8 and has a concentration of X over 24. The outs from tank Y, there is a -2 for the concentration of tank Y and a -6 concentration of tank Y. Now, naturally, these can be added together and you get a -8 Y over 24. Those are basically like terms. So again, this is setting up our model. You can then, this is going to go away. You can simplify a little bit. Yes, this is going to be my tank X model, simplified a little bit. This is my tank Y model, simplified a little bit. And again, there is, in theory, a initial value problem here that we would need to know how much salt is in tank X and how much salt is in tank Y initially. So this would be an initial value problem. And again, notice that this is a system of differential equations. All right, so again, this is just a slight extension on what we learned in section 1.11. Not too difficult, just think clearly about it. So give that a go. There is a second example here. The second example is slightly trickier because I believe some of the flow rates are not balanced. But we did that kind of situation back in section 111. So give the second one a go as well. All right, so this is just an example of again, an actual application that would result in a system of equations. So our question then would be naturally, so how do you solve such a thing? How do we solve a system of DEs? And again, this is analogous to solving systems of linear equations as well. The more obvious idea is to use a substitution method. Solve one of the equations for a variable and substitute it into the other. So let's take a look at, so that is one, let's say that is one method. It's also one method in algebra for solving linear systems. But the more general and applicable method is an elimination method. So there's a quick example here of a substitution to solve this DE. The limits of substitution is it doesn't always work. It's not always easy or possible to figure out how to substitute one into the other. in a DE situation. So this does work for this particular example, but this is not a universal method. So this is not going to be the method for our section. So let me just run through this fairly quickly. You might take a read of this out of interest. We will solve this DE system of DEs using elimination a little later as well. But again, the logic here would be as follows. In order to solve something like this, I'm probably better off by clearing out the fractions here. So I multiplied equation 1 through by 12. I multiply equation 2 through by 3. And so my system could be transformed into a system like this. So in this particular case, I was actually able to set up a substitution, because if you look at equation number 2 here, it is actually possible to solve equation number 2 for x. There is no x prime there or anything, so I can just solve this for x itself. I can then take the derivative on both sides once, so x prime is 3y double prime plus y prime, and then that I can actually substitute into number 1. I can substitute this into number 1, and this gives me basically a differential equation in y only. So it's actually a second order differential equation for y. This is what it might look like initially, and then you can kind of clean it up and try and solve it. So I cleaned it up a little bit. This ended up being our DE. This is a homogeneous second order. So again, this all depends on the characteristic equation and the roots, and that can be solved. So I solved for y here. You can attempt to go back and solve for x in a similar fashion, and then you'd have to sort out the constants. But again, this is not going to be our general approach here, so this is a little limited. So we are actually going to concentrate on an elimination method for solving systems of equations. So the first thing I'm going to have you do is, just as a reminder, hopefully this is nice and easy, remember how to solve a system of equations, just in algebra, linear algebra, systems of linear equations. How will you solve them by an elimination method? So again, this should seem fairly easy, but here's just a warm up, a brush up on how to do that. Okay, so now the question is, how do we set up an elimination method for systems of linear differential equations? The answer is, in order to do this, we are going to use something called the derivative operator or the differential operator. We're going to call it D for this section. Notice that D is nothing more than what we have called in Calc 1, and through calculus, we just call it d dx. So we've often used this notation in calculus to indicate the idea that we are telling you to take a derivative of something. So we could have just used d dx here, but it's kind of awkward to write and a bit messier to write. So we're going to simplify it and just call it d. So some examples here. What would be d of x squared, dx squared? Again, notationally, what do we mean here? And again, we're not going to write this just for brevity, but what we really mean here is that this is d acting on x squared. This is the same thing as saying, take the derivative of x squared. So the answer is indeed 2x. That's all this means, all right? It gets a little stranger looking when we write it this way, when we write things like this. What is d minus 2 acting on x, or d minus 2x? But again, we can actually distribute here as you would if it were algebra. And again, this is a bit of an issue we will talk about, but I can do d times x minus 2 times x, dx minus 2x. dx is 1 and 2x, so we get 1 minus 2x here. Here is another one. What is this guy here? This is d squared minus 2d plus 1. And again, just distribute. This is d squared y minus 2dy or d2y plus 1y. So d2y says take the second derivative of y. So you'll see this slowly. d is d squared. Yes, it just says take the derivative and take another derivative. So dd acting on y is y squared. The d acting on well, minus 2d acting on y is minus 2y prime, and 1 times y is y. So this is the very same expression as this is what we're intending here. All right, this next one is a bit more interesting. There's a couple of choices here, yes. We can do, so what is d plus 1 times d minus 5 acting on y? Well, one way to do this is just to do it in stages, right? Do this guy first, and then apply the d plus 1. So that's what I'm doing here. If I do d minus 5 acting on y first, we would have y prime minus 5y. And then if we do d plus 1 acting on this, again, distribute, this would be d, and this is plus 1. So d acting on this would be y double prime minus 5y prime plus y prime minus 5y. This is correct. We can clean it up a little bit. This would be the correct equation here. But notice the other option is to FOIL out d squared minus 4d, excuse me, to FOIL out d plus 1, d minus 5. If you FOIL this out, you get this guy. And if you act this on y, we indeed get the very same thing. So this is kind of a curious thing, yes? There is really no particular reason to assume algebra like FOIL works on something like this, because D is not a variable, D is not a quantity, D is an operation, right? It's just an operator telling you to do something. However, it does seem to work in this case. The big picture here is it turns out that this sort of thing works as long as we only have constant coefficients that we're dealing with. We cannot have functions of the independent variable, probably a function of t here. You cannot have those, because then this idea of doing algebra with differential operators starts falling apart and does not work. All right, so here's a little example for you to try it, an example to like these and try the differential operator. All right, so briefly, let me go to my other document here real quick. Again, this is some of the discussion here is being repeated, but just wanted to show you some other little examples here. Notice that again, we are familiar with the operator as either ddx or ddt. Notice in those examples we just completed, we did not actually know what the name of the independent variable was. We were just differentiating. There might be times when I would need to know, but again, d is just the derivative with respect to the independent variable, whatever it is. Again, we will not call it ddt, we will just use d. So if the independent variable is t, then we can do things like these, yes? D acting on t squared is just telling you to take the derivative. D acting on 3t is just telling you to take the derivative. Again, important here in this notation here, if x is a function of t and y is a function of t, then derivative is being done with respect to t. So what is d acting on x? It is not 1, it is x prime, right? We would assume the derivative is with respect to the independent variable t. Similarly for y, the derivative of y would be y prime. And again, we mentioned this, d squared x is d dx. So take the first derivative and get x prime, take another derivative, get x double prime. So we can, again, we can do some algebra with these. So here's a little demonstration again. Here's a simple example. Here's an example that you can do algebra with these differential operators, as long as we don't have any functions of t involved. This is okay and works out. Down below here is a little example just to demonstrate that, yes, the one above we just did, this works out by either method, right? I can do d minus 4 acting on 2x first, and then d plus 2 acting on the d minus, excuse me, d, this should be a typo. This should be d plus 3 acting on the result. This should work by either doing them one by one or by foiling it out and doing it all at once. This works out fine in this one because there are no independent variables present. But if you are doing the same operation acting on something with an independent variable, now this is a bit of a problem because t is the independent variable, x is a function of t. Differentiating things like this requires the product rule, and things become a mess and don't actually work out anymore. So that is what we are worried about. Hence, as we noted, we can only do this for constant coefficients. All right, so a little example, trying out an example, something like this, or applying a differential operator to an equation, I believe. So give that a go. Okay, so going back to our notes. Again, a little explanation of why we say we can only do this with constant coefficients. So we will be limited to systems of equations with constant coefficients only. Linear, constant coefficients only. So a couple more examples here. We're going to use this differential operator in order to set up an elimination process. What the differential operator does for us is kind of allow us to combine dx dt and x and make a single term out of them. So things like this, if we read dx dt plus 2x equals 5, we can actually rewrite this using the derivative operator as d plus 2 acting on x equals 5. And the point is that this used to be two things, dx dt plus 2x. This is now a single x term when written with our differential operator. Similarly with y, we can apply or rewrite this using our differential operator. This is fairly easy. I'm really just working on the left-hand side here and rewriting this as 2d squared minus 3d plus 1. Right, and then this, instead of being 3 terms for y, is now a single y term. And this is why this is valuable to us. So we're actually going to need to do things like this next one. Here is an equation involving x's and y's, but notice then I can rearrange this equation so that it has an x term and a y term and then equals everything else on the other side. So we can rewrite x squared minus 2x as d squared minus 2 acting on x, and y prime plus y is d plus 1 acting on y t. So now we have an x term plus a y term equals numbers on the other side. This is what we always wanted in an elimination method. We wanted, even back in algebra, we wanted to organize things so that the x variables came first, and then plus or minus the y variables, and then the equal sign, and then everything else, all the numbers on the other side. So this is our DE equivalent of that. So this is an important situation that we are going to need to be able to use in order to set up an elimination method. So give one of these a go in my open math. All right, then let's see actually solving a system of DEs by systematic elimination. So this first one is a fairly easy one, easy in rabbit ears because these can be quite involved. So even the easy ones take a bit of work. But if you're into that kind of thing, they're kind of fun. All right, so this is our method. We are to solve the system of DEs by systematic elimination. So we really have two equations here, number 1 and number 2. The first one is dx dt minus 4y equals 1. The other one is dy dt plus x equals 2. This is not written in a convenient way for our purposes. First off, I don't have it organized as I want. I don't have the x's first in both equations. I don't have the y's second in both equations, and then everything else. I do have all the numbers on the other side, so that works out. But this would be my first process, is I am not going to worry about dx dt. We're just going to write d instead. But I'm going to first rewrite both of these equations using the derivative operator d. So the first one is dx minus 4y, no derivative there, equals 1 on the other side. The second one, I am going to use my derivative operator, but also organize them. So I'm going to move the x in front so that my x's line up first. And then I have the x first, and then I have the x first, and then the dy second equals the number on the other side. So this is my first step here, and that is I really want to rewrite this and re-envision this linear system of DEs in this fashion. Once I have it in this fashion, I can think about setting up the elimination. So remember, with an elimination, we're trying to multiply by something. And again, I'm going to use multiply loosely here. What we're actually multiplying by here is some sort of expression in D. So we're going to need to turn one of these. I'm going to either, if I want to eliminate the x's, I need to make these match up, right? Make these two look the same, but with opposite signs. So it does look easier to eliminate the x initially. We could eliminate the y without too much trouble. But let's think about eliminating the x initially. This would require that I multiply through the second DE by minus D. And again, multiply is probably not the best word here because D is not a quantity, right? It's an operation. But I need to apply minus D on the second equation. So the first equation is untouched, and then I'm going to do a minus D through the second equation. So that gives me a minus dx, and then a minus d squared y, and then on the right-hand side, I get a minus d acting on 2. What is the derivative of 2? It is 0. So this one just becomes 0. So at that point, these match up. We can add the two equations together, and we will eliminate those x's and end up with a dE in y only, namely minus d squared y. So we are adding, so minus d squared y minus 4y, and then 1 plus 0 is 1. This would be our dE. And again, we can then apply the derivative operator. This is a minus y double prime minus 4y equals 1. I can multiply through by -1 to make it look a little nicer. And so we are down to having a second order non-homogeneous equation for y here. So this is, while as subtle as this looks, this is non-homogeneous, yes? So we do need to work through the non-homogeneous process. So again, let me be brief here. Again, we can see the characteristic equation. We can solve for its roots. Using those roots, we can set up the complementary function. We then need to find a particular solution. There are no duplicates here, so I do not need to adjust my guess. My guess can simply be a constant a. We can plug in a and its first and second derivatives and solve for a. I get a equals -1/4. Hence, the solution for y is the complementary solution plus the particular solution as we already know. So this is our y. So we are not done yet. The next issue then becomes, how do we find x? We actually have a couple of choices here. Again, one choice I think work-wise is preferable, but not universal. The other choice is a lot more work and a little harder to follow through. So I do prefer, wherever possible, I'm going to try to do the easier method. And that is just to back substitute y in order to solve for x. So I just need to come back to my equations here. And I simply have to ask myself, can I put y back in to solve for x anywhere? So I would argue that if we're looking at equation number 2, equation number 2 can be written as x is 2 minus y prime. So if I do y prime from the y I just found, plug that in, then I have an equation. So clean it up a little bit. Then I have a solution for x. So this is what I recommend to start with anyway. Again, sometimes this doesn't work very nicely, but we can go back to our original system and look for a way to back substitute y. It might need to back substitute y prime. Maybe we need to back substitute y and y prime. But the idea would be I could use either equation. And in fact, I can also use any linear combination of these two equations. So I could, for example, add these two equations together and substitute into that if that was easier. But that wasn't necessary here. Number 2, solve for x, worked rather nicely. So there we have a general solution to this system of equations. You could then, if asked, and a lot of your homework questions do ask, you can solve for an initial value problem if needed. And again, an initial value problem is really just going to give you a condition for, a condition for y, a condition for x. This should give you an equation, 2 equations for C1 and C2, so you can solve a little linear system of equations to find them. So yeah, this was an easy one, and it is still a fair amount of work, yes. So these can be fairly kind of time consuming. All right, just before we go, I'd like to just talk through the setup of the next one. We will still do this one in class together, but let me just point a couple things out here. This is actually solving our original mixing tank problem, yes? This is that same DE we started with. Same system of DEs we started with. This is what we did before, where we multiplied to get rid of our fractions, clear the fractions. And again, at that point, I can think about setting these up in terms of a systematic elimination. But again, what I want to do then is gather the x's first. So the x's first, and then the y's second in each equation. And then we can rewrite the system in terms of this D operator. So 12x prime plus 4x is 12d plus 4x. And down here we have a minus x. And then again, we can write out this system this way. So the only reason for looking at this one is that this is actually probably more typical, that to eliminate here, I could probably eliminate either the x's or the y's. I think the work-wise, the setup looks about the same. I chose to eliminate the x's here, and then that means I need this term and this term to be the same term, but opposite signs. So I'm just going to multiply through. This is already the opposite sign. So I just multiply through the second DE all the way through by 12d plus 4. So we would get, again, the first equation is unchanged. The second equation we multiply through by 12d plus 4. We can then add these together, eliminating the x's, and then we would get a DE for y by itself that you can solve. So that's basically, I just wanted to point that out. This is probably more typical that we're going to be working with a term that looks like this, right? This is a single x term, but with a binomial operator. All right, so there are a couple of examples for you to try on the website of actually solving these. So give the first one a go. And then there is a second one to try as well. So try that. And that's it. So that will be it for our video today. We will then pick up this and solve example 3 onwards together in class. See you there.